The Rocky Mountains, the backbone of North America. Rugged, spectacular, and majestic. Today, geologists are cracking open these rocks to expose their secrets. How did the remains of sea creatures end up in mountain peaks, thousands of feet in the air? When did the Rockies form? Are they still rising today? And if they are, could the great forces that built the Rockies one day split North America in two? The Rockies, one of the greatest mountain chains on Earth. They stretch over 2,000 miles from the northern tip of British Columbia to the Rio Grande in New Mexico. Up to 300 miles wide, they form the Continental Divide, the great barrier between east and west. In Colorado alone, there are 58 mountain peaks over 14,000 feet tall. That's around 2.5 miles high. The Rockies were created by the most powerful geologic forces on Earth. Their dramatic story takes us on a journey from north to south through 200 million years of geological history. From their birthplace in Canada to the youngest peaks in the United States. It's a journey that takes us back into the Earth's ancient past. 200 million years ago, there were no Rockies. Even the continents looked different. There was just one giant landmass, Pangaea. But not for much longer. A vast rift is opening up, tearing this supercontinent apart. Over the next few million years, Pangaea will break apart into many smaller landmasses, eventually forming the present-day continent of North America. Earth's surface is broken up into vast pieces called plates. They sit on top of the Earth's warm, dense mantle. As the planet gradually cools, convection currents in the mantle slowly move these plates across the surface of the Earth. Where plates meet at their edges, there are often immense tectonic forces. These tensions can tear continents apart, but they also build mountains. Kirk Johnson, chief curator of the Denver Museum of Nature and Science, explains.
The action of continents crushing together or continents being hit by oceanic plates, those kinds of forces create basically planetary traffic accidents, and the wrecks result in mountains forming.
Evidence of the power of these immense forces can be found in one of the oldest and most northerly parts of the Rockies, Yoho National Park in British Columbia. Here, the fossils of thousands of peculiar prehistoric creatures lie in a cliff face near the peak of Mount Stephen, 8,000 feet above sea level. Geologist and mountain guide Paul McNeil specializes in the fossils of the Burgess Shale.
We see fossils here that we find almost nowhere else in the fossil record, and unlike any animal that's alive today.
This spiny creature is called Hallucigenia. And this bizarre specimen, Wiwaxia. These fossils offer clues to how the early northern Rockies formed, because they're not the remains of mountain-dwelling animals, but of sea creatures. They lived and died in a shallow tropical sea over 500 million years ago. The rocks that contain these extraordinary fossils formed on the sea floor.
Right around us, all of the rocks that we see used to be part of an ancient seabed. The limestones were part of the continental shelf, the shales were part of the deeper ocean waters, but it was all underwater.
Long before the Rockies formed, the west coast of North America was covered by a shallow sea. Over millions of years, clay, mud, and gravel settled on this coastal shelf, trapping and fossilizing tens of thousands of sea creatures. Layers of sediment solidified into rock up to 12 miles thick. The rock layers in this cliff are made from sediment laid down over 8,000 years. Today, these fossils are 1.5 miles above sea level. But once they were buried 6 miles under other layers of rock.
At their deepest point, these fossils were buried over 10 kilometers under the Earth's crust. And since then, they've been thrust up to over 2 kilometers up into the air, where we actually find them now.
This ancient rock formed offshore, 400 miles west of here. So what could have driven this ancient seafloor so far inland? And what pushed it up almost 8 miles? A force powerful enough to transform a flat ocean floor into massive mountains. Subduction. 180 million years ago, the North American plate was moving west, driven by the breakup of Pangaea, and the Pacific Ocean plate was heading east. The two colossal plates met head-on. In this clash of the titans, the denser Pacific Ocean plate was forced down beneath the more buoyant North American plate. Professor John Geisman from the University of New Mexico demonstrates.
What I'm going to do is simply tap on one of the sides, and I'm going to create an instability. Now we have oil starting to migrate, move its way over the top of the CD. Ah, voila, it's happening all by itself. I don't have to nudge it anymore. You see the oil moving its way across the CD like so, and the CD itself is going to begin to move like so into the oil, and the subduction process is completed. It's subducted into the interior of our planet, if you will. And it's a runaway process. You can't stop it.
On top of the subducting Pacific plate sat offshore islands. As the plate was pushed eastward, it carried these islands like a conveyor belt. One particularly large island reached the junction of the two plates and coast of North America, but it was too large and buoyant to be pushed down into the mantle. Instead, it slammed into the continental shelf on the western edge of the continent. The seabed was shoved eastward. It slowly folded up like a crumpled carpet. The fossils of the Burgess Shale were pushed thousands of feet into the air and miles inland. Geologist and author Ben Gadd has spent 30 years studying the Rockies here in British Columbia.
One way to imagine this whole pushing and shoving business is to do it on your hands. So you have the bony part of your hand, and then you have the skin over the top, right? So imagine that the bony part is the continental plate, and on top of that, you have all the sedimentary layers, right? That's the skin. So when the big push and shove comes, you have the skin being pushed along the bony layer, and as it gets pushed along, it wrinkles up. That's a good analogy for how the Rockies were formed. The older I get, the better this works for some reason.
Over millions of years, the plate collision forced up the northern Rockies. When the force of this collision lost its power, the first wave of mountain building came to an end. But that's not the end of the story. 80 million years after the first block of land hit the coast, a second one slammed into its back. It bulldozed everything eastward and upward. Layer after layer of rock was shoved higher and higher. First into hills, and then into mountains. Gentle folds of rock evolved into the mighty Rockies. Today, these slabs of land, called terrains, make up British Columbia. As they continued to rise, the Rockies were continually sculpted by the momentous force of the elements. Even as they were pushed up, erosion was starting to tear them down. The Canadian Rockies. Jagged peaks, steep cliffs, and razor-sharp ridges, carved from the sedimentary rock of an ancient seabed. Despite being caught in a mighty plate collision and thrust up into towering peaks, the layers of rock in these mountains still lie almost horizontally. This provides a clue about how they rose up. As the blocks of land drove into the coast of North America, slabs of sedimentary rock were pressurized and folded so much that they snapped. Broken sheets of rock, up to a mile thick, shunted forwards and slid over each other again and again, in a process scientists call thrust faulting.
So the rock has actually been folded to the point where it can't be folded anymore. And at that point, the upper part of the fold will literally break and start sliding along. That's what we call a thrust fault. And it's a classic kind of fault for the Canadian Rockies.
Sedimentary rock forms when younger layers of sediment settle on top of older layers. But here in the Rockies, layers of different ages are jumbled up. Thrust faulting pushed older layers of sedimentary rock up and over younger layers.
Suppose that we think of this book as being a continuation of the layered rock that we see here. Now in a thrust fault, what happens is this part will break up and it will slide along like this, and it can go rather a long way until eventually it stops. So now we have layers that were down here pushed up over these layers. Old rock pushed up and over younger rock.
In this laboratory sandbox, the layers of colored sand represent layers of sedimentary rock. As the sand pushes eastward to the right, thrust faults form, one in front of the other. Thrust faulting pushes older rock layers above younger to create the distinctive sawtooth ranges of the northern Rockies. These mountains first emerged 140 million years ago. Thrust faulting first built the western ranges, and then crept eastward, forming a new range further inland. 120 million years ago, the main ranges appeared. And then even further east, the front ranges, 85 million years ago. Thrust faulting began to slow down until eventually, 50 million years ago, it stopped. At Mount Yamnuska, the mountains and the foothills meet. Beyond lie the flat plains of Alberta and Montana. Immense forces pushed an ancient seabed thousands of feet into the air. But a very different force sculpted it into these striking peaks. Erosion. Evidence of erosion's power is strewn all over the mountainside. Piles of broken shale and heaps of ash-colored sediment called scree.
Erosion has been at least as important as the mountain building itself. It's the mountain building process, the uppiling, that gives you the elevation to give you the height of the landscape, but then the landscape itself is carved downward differentially. So erosion is very important. It actually gives us the landscape we see.
Erosion is so powerful that it has scraped up to 2 miles of solid rock off the top of these mountain peaks. And the main force of erosion is water.
Water loosens material, sends it downhill. Water dissolves minerals. Water freezes and breaks up the rocks.
The northern Rockies are made of sedimentary rock like sandstone, shale, and limestone. Relatively soft and soluble, these are easy prey for erosion. And here in Canada, water's erosive power takes on a new dimension. In this cold climate, snowfall freezes and compacts to form enormous sheets of ice, glaciers. The glaciers here creep forward at 50 feet per year. On a geologic timescale, this is fast. Glaciers pick up and carry loose rocks and boulders, which scour and scratch the rock beneath them. Like giant ice cream scoops, glaciers gouge out distinctive U-shaped valleys. And when they melt, they leave behind deep gorges and steep-sided peaks. Erosion has worn down these rocks over millions of years. But the Rockies are fighting back. While erosion attacks their summits, deep below ground, the mountains are still growing. Look at the Rockies, and it's like seeing the tip of an iceberg. Mountains have roots, which can be 5 or 6 times deeper than their height. This mountain stands over 2 miles high, but its hidden root could extend 13 miles underground. These roots are the Rockies' secret defense against erosion. Structural geologist Carl Karlstrom from the University of New Mexico demonstrates using blocks of ice. The red and green ice layers represent the mountains above ground, and the white ice their roots below ground.
Mountains are not static things. The Earth's surface is continually being reshaped by erosion, by rivers, by glaciers that tear the mountains down. So let's imagine I'm eroding the mountains now, and I'll just pull one of the blocks off. The overall surface has gone down. The continent has gotten thinner, its roots come up, and now this rock, which was deep in the earth a minute ago, underneath the green layer, has come to the surface. That's called rock uplift. So I guess I'll erode off the pink layer too. We're back down to a continent without a major mountain belt, something like the eastern part of North America.
When the heavy weight of the mountain is eroded away, the root rebounds upward. This process means that the Rockies are constantly topped up from beneath. In Canada, thrust faulting and erosion have shaped the mountains. But as we travel south, this distinctive landscape is about to change. Just south of the US border in the state of Montana, a new rock appears among the Rockies: granite. This is the first clue that the mountains of the American Rockies are radically different. On our journey south along the Rocky Mountains, we're entering a very different landscape. From Montana southward, the Rockies are made from ancient granite, 1.7 billion years old. Granite makes up much of the deepest part of the continental crust. That's why geologists call this rock the basement. The Canadian Rockies are built from sedimentary rocks piled up on top of the continental foundations. So why does granite suddenly appear here in the American Rockies? But there's an even greater puzzle. Mountains usually form close to plate boundaries, but the southern Rockies sit a long way from the plate margin. The Front Range in Colorado is 1,000 miles from where the Pacific and North American plates actually meet. Geologists have come up with an explanation. They believe that the subducting Pacific Ocean plate is responsible. Ocean crust had been pushed deep into the mantle beneath North America for 100 million years when something unusual happened. 70 million years ago, the Pacific Ocean plate started to subduct at a shallower angle. Instead of plummeting steeply, it sliced beneath North America horizontally. This change had dramatic consequences.
The big oceanic plate in the Pacific didn't go deep down, it went in shallow like a spatula under a pizza. So something happened 68 million years ago over in California. That plate drives under North America, but instead of diving deeply, it comes in shallow, and 1,000 miles away from the coast, up from the ground, sprout the Rocky Mountains.
For millions of years, the ocean plate scraped along the underside of North America. It created friction, breaking up the basement granite of the North American plate and punching it upward. Structural geologist Carl Karlstrom demonstrates.
Because it was at a shallower angle beneath North America, it was scraping along the base of North America. When that happens, it puts the plate under compression like this, because it's being both pushed at the end and scraped along at the bottom. So it squeezes, pushes up the mountains, and it transferred this mountain building from the edge to great distance from the plate margin.
The shallow angle trajectory of the Pacific Ocean plate explains why these mountains formed so far inland. And it also explains the presence of granite. Thrust up through layers of sedimentary rock, the broken granite became the Rocky Mountains of the South. Red Rocks Park, Denver, Colorado. A landscape forged by granite uplift. Kirk Johnson demonstrates how these granite peaks punched up through the layers of red rock around them.
I'm going to use my assistants, Veronica and Ian, to help me explain how the Rocky Mountains in Colorado formed. Imagine, if you will, that Veronica and Ian are composed of 1.7 billion-year-old metamorphic rocks, the basement rock of Colorado.
Before the mountains grew, layers of sedimentary rock covered the granite.
And then about 68 million years ago, the mountain where Ian is starts to break and lift up and move up. So you see the uplift forming. And what's happening is that layer of sediments being deformed and bent. And these are the flat irons at Red Rocks. As the mountain comes up, overlying sediments are eroded off and deposited into the adjacent basin. And eventually, Ian's granitic back is exposed as the core of the Rocky Mountains. Veronica remains deeply buried beneath Denver, still covered with deep sediments, and the sediments eroded off the uplifting Rocky Mountains.
Johnson is investigating exactly when these events took place. He focuses on the Colorado Rockies Front Range, which runs 350 miles between North and South Colorado. Dating the Rockies requires real detective work. And like all detective work, you get clues by digging up dirt.
Yeah, so it's sort of counterintuitive. To understand mountains, you don't look at the mountains necessarily, you look at the debris from those mountains. So just like a detective would go through a criminal's garbage can, the basin adjacent to the mountain range is sort of a garbage can of the adjacent mountains. The mountain goes up, it sheds all its garbage off to the side, in this case sedimentary rock and fossils, volcanic ash beds, layers of lava. We can look at that garbage and reconstruct the chronology of the uplifting mountain range.
Today, this debris forms layers of sediment 10,000 feet thick beneath the city of Denver. In their mission to date these massive peaks, Johnson and his colleagues search for the tiniest clues, like fossilized leaves and pollen. For Doug Nichols from the Denver Museum of Nature and Science, these microscopic grains of pollen provide a valuable lead.
Pollen can be used to date the uplift of mountains because plants that were living at the time the mountains were coming up were shedding their pollen, which was becoming incorporated into sediment, which was being eroded from those same mountains. And I'm looking for the particular species of pollen that can tell me the age of the sample.
Each sample of sediment can contain thousands of fossilized pollen particles. Nichols examines a single grain. Every plant genus has distinctive shaped pollen. So by identifying the species of plant and its age, Nichols can start to date the exact uplift of Colorado's Rockies.
We pretty well understand that the uplift began 65 to 70 million years ago because we find distinctive kinds of pollen produced by plants that only lived 65 to 70 million years ago.
Sometime during this 5 million year period, Colorado's Rockies began to rise. But geologists can narrow this window even further, thanks to one of the most catastrophic events in history. $65.5 million years ago, an asteroid smashed into the Earth. It wiped out the dinosaurs and left a distinctive line in the sediments by Colorado's Rocky Mountains. This pale yellow layer in the rock contains the remains of the huge asteroid. Because it's sandwiched between layers of debris that eroded off the Rockies, we know that the Rockies must have been up and eroding at the time of impact, 65.5 million years ago. Kirk Johnson specializes in dating fossilized leaves. He uses them to date the Rockies' birth even more precisely. Geologists know that 69 million years ago, Colorado was covered by a shallow sea. But Johnson's fossil leaves show that just a million years later, there were plants here. Johnson combines his findings with Nichols' pollen evidence to come up with a million-year window during which the Colorado Rockies must have emerged. And compared with the northern Rockies, these mountains grew up fast.
We know that 69 million years ago, Colorado was covered by a shallow sea. We know that at 68 million years ago, the Rocky Mountains were up. So sometime in that 1 million period, 1 million years, the Rocky Mountains came up. It may have taken all the 1 million years. It may have happened in 200,000 years. We don't know that yet, but we're working on that particular question.
Although Johnson's team can't yet say how quickly the mountains grew, they are certain of one thing. 68 million years ago, the American Rockies had arrived. As we continue south through the Rockies, the landscape evolves once again. 35 million years ago, at the southern tip of the mountain chain, volcanoes appeared among the peaks, triggered by changes deep beneath America. A new explosive era had begun. As we travel south 2,000 miles through the Rockies and forward through their 200 million year history, we reach Albuquerque, New Mexico. Here, a dramatic change deep beneath America triggered the most explosive phase in the evolution of the Rockies. "70 million years ago, the subducting Pacific Ocean plate punched up huge blocks of basement granite, forming the Rockies of New Mexico. "35 million years later, the Pacific Ocean plate began to peel away from the underside of the North American continent. As the ocean plate sunk deeper, warm mantle came into contact with the underside of the North American plate, right underneath parts of the southern Rocky Mountains. Just as the burner on a hot air balloon makes the air less dense, causing the balloon to float upward through the cooler air around it, so warm, buoyant mantle rose up through the cooler, denser mantle beneath the mountains. Carl Karlstrom thinks that this caused the Rockies to grow even taller.
Well, let's think about uplift of mountains in the context of this analogy of a hot air balloon. We're floating high because we're more buoyant than the air around us. And if we want to go up, actually get still higher, we'll just turn on the burner and fire it up, and then the air becomes lighter within the balloon, causing a dynamic or an active uplift. And we can think of that in the context of mountains as if an upwelling of warm and buoyant mantle is actually pushing up the mountains.
But it's not just the mountains that were affected. The upwelling mantle also stretched the crust above. This sandbox simulation demonstrates the stretching process. As the continent pulled apart, the crust thinned and fractured. An immense crevice, called the Rio Grande Rift, opened up in the heart of the Rockies. In parts of the southern Rockies, the crust is over 30 miles thick, but in places beneath the rift, it's just 17 miles thick. This thin crust triggered something dramatic. Under immense pressure from rising heat in the mantle, it gave way. Red-hot magma blasted out onto the New Mexico landscape. And volcanoes punctured the Rio Grande Rift. Scientists believe that hot magma has surged up from the mantle many times over the past 35 million years. These surges led to renewed volcanism in the Rio Grande Rift. But this is not ancient history. The last eruption, just 1,500 years ago, flooded New Mexico with a river of molten lava 44 miles long. Could such recent eruptions mean that hot magma is ballooning beneath Earth's surface today? Could the Rockies of New Mexico still be on the rise? Laura Crossi, a geologist at the University of New Mexico, is on a mission to find out. Working with Carl Karlstrom, Crossi is focusing on a fault where the Rio Grande Rift meets the Rockies. Here, hot springs bubble up to the surface from deep below. Gases in the water can provide a clue to the activity in the mantle.
This point along this fault is a place where these fluids are finding their way to the surface because of the extension, the tectonic activity. We're able to come here and have a window into that deep, deep world, all the way to the mantle.
Beneath Earth's surface, gases are under immense pressure and dissolve in water. When they reach the surface, they escape as bubbles. Analyzing samples of the gas bubbles, Crossy discovers carbon dioxide and traces of helium-3. Carbon dioxide and helium-3 are both byproducts of activity in the mantle. Their presence indicates that deep beneath the surface, rock in the mantle is melting and on the move. Like a rising hot air balloon, hot, buoyant magma is slowly surging up beneath both the rift and the Rockies. This is evidence that here in New Mexico, the Rocky Mountains are far from dead. They could still be growing, thrust higher by rising mantle. Karlstrom believes that in the future, there will be a wider rift and taller, more spectacular Rockies.
I think portions of the Rocky Mountains are going up dynamically, and that they are getting higher, and the Rockies are getting higher, and certainly in the million-year time frame, we will have more interesting, higher, and more rugged mountains, I would predict.
Having investigated their past, geologists are now looking to their future, and it's bleak. The Rockies are doomed, and North America's destiny hangs in the balance. On this journey through the Rocky Mountains' 200 million year history, we've witnessed their dramatic birth and examined their complex evolution. Now we turn to their uncertain future, a future that goes hand in hand with the fate of the whole North American continent. This is the Columbia Icefield in Alberta, Canada, where geologists are already seeing how the mountains are changing. Within 100 years, it could look something like this. Human activity is altering the course of geological history. Increasing global temperatures are taking their toll on the mountain's glaciers. They're melting. Brian Luckman from the University of Western Ontario wants to know how fast. During the winter, glaciers grow. An advancing glacier pushes a pile of eroded rubble ahead of itself, called a moraine. When the glacier shrinks back in summer, it leaves behind this pile of debris in its wake. It's a telltale sign that the glacier is melting away.
Because the glacier over time is retreating continuously, then what you have left are a series of these annual moraine ridges, which mark the furthest point of advance during the previous winter.
Luckman walks between the moraines, using GPS to map the distance between each one. The greater the distance between them, the faster the glacier is melting.
Glaciers are one of the most effective ways to demonstrate to people that the climate is changing. You've only got to come here twice or look at some of the older photographs to realize something radically is changing.
These two photographs of the 3.5-mile-long Athabasca Glacier show how far it has retreated over the past 30 years. And these photos of the Grinnell Glacier in Montana show that America's glaciers are disappearing as well. One day, the glaciers that have shaped these steep-sided peaks and U-shaped valleys will disappear. But water erosion will continue to sculpt these mountains, beating them down and softening their jagged edges.
The future of the Rockies is that they're eroding at the rate of about 0.06 of a millimeter per year. This is based on taking a sample of river water, measuring the sediment in it, and seeing how fast the Rockies are being carried off to the sea.
The relentless force of erosion has sealed the fate of the Rocky Mountains since they first began to rise. One day, they will erode away to nothing.
The Rockies that we see today, the beautiful mountains, why tourists come here, why it's just one of the most dramatic places on the earth, they're eroding away. And so if we look at all the rivers draining off of them, they're full of silt and sand, and that is our Rockies slowly bleeding to death.
The Rockies will eventually dissolve away. But far in the distant future, there could be a final devastating twist to their story. A continent ripped in two. The future of the Rocky Mountains is inevitable. Thanks to the relentless force of erosion, they will one day disappear. But they will leave a legacy. The Rio Grande Rift. A great tear in the Earth's crust that could one day split North America in two. Geologist Mizumi Roy and her colleague Nicholas George, both from the University of New Mexico, are taking part in an ambitious 5-year project. Its aim? To monitor the widening of the Rio Grande Rift. The team is setting up GPS stations along the length of the rift, like this one in remote New Mexico, 3 hours from Albuquerque. The GPS receivers are buried in the bedrock to a depth of around 5 feet. When the Earth moves, the receivers move too. Roy explains.
If you have 2 GPS stations, then you have information about relative motion along a line that connects the 2 stations.
A network of GPS stations allows the team to build up a much more detailed map of the rift's motions.
By looking at the difference between the coordinates between the GPS stations through time, we get a good idea of the relative motion between each of these stations.
The team has set up 24 GPS stations along the Rio Grande Rift. It's early days, but the team expects to find that the rift is widening between 0.5 and 2 millimeters every year. It's a very slow process. But little by little, the continent is being unzipped.
The Rio Grande Rift is a rift system that's causing a continent to split. And if this process continues for tens of millions of years, you could eventually rift the North American continent apart.
There's a lot of indications that there's some action happening. Maybe some more is in the future for the Rocky Mountains, and another few million years and there'll be greater tales to tell of active tectonism further to the north, where this Rio Grande Rift is trying to work its way and crack the continent. I think it'll be unsuccessful in that attempt, but it's giving it a good show.
The story of the Rocky Mountains began with the birth of the North American continent. And it could end with its death. One day, the Rio Grande Rift may split a continent. North America might become East and West America. But all this is hundreds of millions of years into the uncertain future. Today, the iconic Rockies are in their prime. The mountains that divide a continent unite us all in admiration. Dramatic and resilient, they will remain the backbone of North America for millions of years to come.